Hyvää iltapäivää. Good afternoon. We will start today a new concept concerning trigonometric equations, and I will add the title in this paper. Trigonometric equations. And this means equations where there are unknowns inside of the one of the most common trigonometric function, sine or cosine or tangent. And before we can start solving that kind of equations, we need a concept of unit circle. So I will let's say what to or write what is this in Finnish. This is almost the same. Trigonometriset yhtälöt. Yhtälö is same as equation. And we will take a unit circle first. In Finnish it is yksikkö, ympyrä. Unfortunately, this camera doesn't show the dimensions correctly. I think this does not look like a circle, but I measured it beforehand, and this radius of this circle is about 7.1 centimeters, and from horizontal measurement and also with the vertical measurement, so it looks like a circle in my paper, but no, unfortunately probably not in your screen. Yksikkö is the same as unit, and circle and ympyrä means the same. And this is a circle which has a radius of 1. It is not 1 meter or 1 decimeter or 1 centimeter, but only simple number 1. So it is some kind of theoretical circle there. So this means that I have these kind of grids there in my picture, and this x-axis here, or this horizontal axis here, is so scaled, has such kind of scale that this point here is the point 1.0. X coordinate is 1 and y coordinate is 0. And in the vertical axis here we have point 0.1. So x coordinate is 0 and y coordinate is 1. And if we go round this circle, here we have coordinates -1, 0, and 0, -1. So this is a circle which has center in the origin of the coordinate system or axis, coordinate axis there, and the radius of that circle is 1 unit. That's why it's called unit. Yksi in Finnish means number 1, and yksikkö is unit. Actually, this, if you calculate the number of grids there, I have made this picture so that there is 20 markings there between this 0. Oh, this is origin 0.0. There are 20. Maybe I will calculate them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. there is 1/2 there, and there are still 2, 4, 6, 8, 10. And now I will take an example. I will draw some angle in the picture, and oh, I'm happy to see that one of you have had the profile picture is probably something to do with geometry. I'm not sure if I saw correctly. Well, I will draw some angle here. I will choose angle 40, not 45. It is too simple, but I will take 50 degrees. So I have this measurement equipment here, and I will draw a angle of 50 degrees. It is somewhere here, so I will use red color, and this is about 50 degrees, this angle here. And now I see that I made a bad choice. but no, let's not care about that. Yeah, it's me, yes. So this is 50 degrees. I made a bad choice to taking this 50 degrees for an example, but let's not care about that. We will see why pretty soon. Yes. Sorry for you who are only watching these videos. I'm just enjoying of this chat conversation there. So please forgive me. Now I try to concentrate again to this example. I have the angle of 50 degrees there, and now I will draw there a right angle triangle, so that this will be the hypotenuse of that triangle. So I will use this. I try to be as careful as possible. It's very hard to see because the camera is in front of me, but it is somewhere here. We have here right angle triangle. And if we check the coordinates of this point here, so remember this is a unit circle which has a radius of 1, so that means that the hypotenuse of this right angle triangle is equal is 1 unit. And now if I try to approximate what are those coordinates of this point, let's call that point P. And remember that my grid is there such that this 1 unit is divided to 20 subdivisions. So if I calculate the amount of these or number of these grids here to get to that point, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, almost 13. I would say probably 12.8 the grids there or squares there. Did I say 12.8? 12.8, and 1 unit is 1 divided by 20. So that will give me a decimal number 0.64. So this point here is about, this x coordinate here is about 0.64. Well, it is approximately. And let's do the same with the y coordinate. So this point has coordinate 0.64, and the other one is this y coordinate 2, 4, 6, 8, 10, 12, 14, 15, probably about 15.3, I would say, and 15.3 times 1 divided by 20 is about 0.765. These are only approximate values which I can somehow measure from my picture. So this is y coordinate, it is 0.765. Unfortunately, you can't see probably those axes well enough. I will draw them better. And now we have got the coordinates of this crossing point there. There is this line or half of the line, and it intersects the circle in that point P, and I try to approximate those coordinates with the help of my poor picture. And what are those coordinates there? If I take my calculator and check from my calculator what is cosine of 50 degrees. We had this angle 50 degrees there, and I will take another of my probably 10 calculators. How you find x and y? Could you repeat it? Yeah, of course. There is a length of 1 unit. This radius of this circle is 1 unit, and there are 20 parts there. There are totally 20 parts, sub parts there, and I calculated how many subparts I have there. So, for example, this x coordinate here, there is 10. This mark I calculated that or counted. That is the 10th place. This is 11, 12, and it is not 13, but it is a little bit less than 13. I approximate that it would be 12.8 here. So 12.8 boxes there, and there are totally 20 boxes. And then I did not take this calculator, but now I will take that. I had 12.8, and there were totally 20 of those. And I know that the whole length of that radius is 1. Well, I may multiply this with 1, but this is not necessary because that doesn't change the result. And now I get this 0.64. Of course, I could try to approximate it from the picture also, because there is every 2 boxes or two squares there is exactly 0.1 unit. So if this is 0.5, in this place I have a coordinate 0.6, and the next one would be 0.65, and I could approximate that this is not it is not 0.65 but a little bit less, so I would approximate 0.64. And also this y coordinate there, if I calculate the 5 units, 5 boxes there, or 5 squares, there must be 5 and 1, 2, 3, 4. In Finnish you will learn some Finnish. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 0.5. And now I will continue. This would be 0.6, 0.7 would be there, and 0.75 would be there, and about 0.76 I probably would get. Or if I calculate the number of these grids there is 10, 1, 11, 12, 13, 14, 15. I don't remember what value I used earlier, probably 15.3. So 15.3 divided by 20 is probably that number. 0.765. I'm sorry, this is not so easy to show in the Teams, or well, that is not excuse. I would do this as badly also in class teaching. Well, I was going to use my calculator and check what is cosine 50, and here I use calculator. Cos 50, that gives me 0.64278, etc. So as you see from the picture, we could approximate that the value of cosine is about value of cosine 50 is about 0.64, and as we checked from the calculator, that is a quite good approximation. We got that correct with 2 decimal places. So this number here, this is cosine 50 degrees, or almost the same value. If I could draw this picture better, I could approximate that probably better also. And also sine 50 degrees. If we take calculator and check what value we get if we take sine of 50 degrees, we get that 0. You don't see anything. This kind of numbers, 0.7660, etc. And from the picture, I love you all. Thank you. And as we saw from this picture, we almost got that correct with 3 decimals. Only the third decimal is one short from my approximation from the figure. So what I wanted to show you was that this unit circle is one method to find approximate values from sine or cosine or also tangent. This is not the only reason why I showed this unit circle. We will see later when we are going to these trigonometric equations, then we may use this unit circle also there. You don't need to draw that unit circle so exactly or with this accuracy. Many times it helps if you can only by hand draw some kind of circle and try to approximate what is the size of the value for the sine or cosine, and it helps many times checking some calculations, and also when solving these equations where we have sine, cosine or tangent. We got that sine and cosine, and if you sometimes have wondered why this third trigonometric function is called tangent, if you remember another mathematical concept called tangent, it is the line which touches a curve in one point. I don't remember the correct word in English, but if I draw a tangent line in the right hand side of this unit circle, so it means that the vertical line which goes through this point 1.0, I will do that now. So I will draw that vertical line. I'll take another color so maybe you can see it better. I can't open the pen. Okay, now let's do that. And as I said in the beginning, I made a bad choice when I chose that cosine this angle of 50 degrees, because you can see that our picture does not fit in the, or almost it fits in the paper. I will try to find the tangent line there. This should be a tangent line there, which goes through this point 1.0, and it is a tangent for this circle. And as you see, this red line somewhere it intersects the blue tangent line there. I will try to draw, and it fits in the fits in the paper, but we can't see the actual grids there because it is too high there. I should have chosen a smaller angle there. I don't understand why didn't I did that. Why didn't it pop into my mind that I would be more careful to choose when choosing this angle. But let's take it as it is right now, and we can see that these lines intersect there, and now we should have to approximate what is the length of this line from this point to this point. I can't see those grids there, but I will use my measurements. So I will do like this, because I can see that from my, let's take another ruler, maybe you can see this better. So the circle of the radius of this circle is about 70 millimeters, quite near 70 millimeters, and the intersect line there is the intersection point there is about maybe 84 or 8. I can't see it. I would like to be more. I think 84 or 85. Let's take either of those, and I noticed that it was, or I measured that the radius of the circle was about 70 millimeters in my picture, and I measured the height of this point there, and it was, did I say 84 millimeters, and if I divide this by 70, I will get the answer of 1.2. I don't know, probably it is a little bit more than 84 for that measurement, but let's check. This is this length here. I will use the blue color there. This is about 1.2 in the picture. And then when I take this calculator again and check what is tangent 50 degrees, I hope we get pretty near that number. Well, I'm very glad about this 1.19 or 1.1917, etc. So we may see that we approximated that this value is about 1.2, and now we from the calculator we saw that it is exactly 1.19, etc. So we got this correctly, not with 2 decimals as we did here in sine and cosine, but with 1 decimal. But the error is not so big, and my picture is not so clear because we can't see. I had to make this a little bit differently than these other measurements there. So this is the some kind of uh, what is it? This is how you get those values from sine, cosine, and tangent with the geometric way. But now we are going to these trigonometric equations here, and I want to show you one thing. Earlier in this course we have only used sine or cosine or tangent when we have been solving parts of triangles, either a right angle triangle or oblique triangle. And in those triangles, those angles could be only between 0 and 180 degrees, because in the triangle there the sum of the angles in a triangle is always 180 degrees, and that means that one angle, it is not possible to be more than 180 degrees. But when we are looking at this unit circle, let's take one angle. I'm not going to draw it, but I will take an example. If we had an angle which would be here, let's do this, for example here, that means the angle starts from the positive x-axis here. This is x. And it starts and goes counterclockwise, vastapäivään in Finnish. Is this concept? Clockwise is myötäpäivään. Ja help me. Did I say counterclockwise? I forgot the. Is it like this? Ah, yes, okay. This is vastapäivään in Finnish. Päivä is a day, and this means myötäpäivään. It actually means that it goes like sun goes. It goes to the same direction and as clock or this old-fashioned clock, which we probably not so many have anymore. And this counterclockwise direction is the positive direction of the angle. It is somehow strange. I think most of us, if we had to choose, I think we would have chosen differently. In my opinion, this would like more logical to get the positive direction in the direction of clockwise. But in mathematics we have chosen like this, or I haven't chosen, but someone has chosen it like that. Actually it goes the positive direction, it goes so that it starts from the positive x-axis and goes towards the positive y-axis, and in this picture it goes counterclockwise. if I draw this picture like this, you can't see it, but now the positive x-axis is there and the positive y-axis is there, so the positive direction is to this direction. So this is only the real positive directions goes from positive x-axis towards the positive y-axis. But what I was going to say, that if we have angle, for example here, and the angle would be like this, where I will approximate that it is about 125 degrees probably. And now when we have the angle there, we notice the x and y coordinates with the same method, and now we see that the x coordinate here is negative because it goes to the left, and y coordinate is positive. And because I forget to draw there, this is sine value there, and because the x coordinate tells us the value of cosine and y coordinate tells us the value of sine, then that means that if the angle is here, then the cosine of that angle is negative and sine of that angle is positive. If I check from my calculator, if I take cosine of this about, did I say 100? Let's check that angle again. 125, about 125. It is negative value as you see, minus 0.5. And if the angle goes like this here, then you could see that the intersection point there is here, and it goes left and down, so the both coordinates are negative there. So both cosine and both sine gets negative values. This angle maybe, because this is 180 degrees and this is about 30 degrees more, so this is the angle of this line here would be about 210 degrees about. And if I check what is the value of cosine 210, we got this, so that is negative value, and also sine 210. This gets all I have used not this calculator so much, so it is also negative value. And then this fourth quadrant, this is first quadrant, second quadrant, third quadrant, and fourth quadrant. And here the angles are so that the intersection points gets positive x coordinate but negative y coordinate. So cosine is positive and sine is negative. But then we could also continue this rounding around this circle here. So we could go first round, second round, etc., and we may continue this how long we want. We don't need stop anywhere there. But we can see that if we are rounding this one circle or one round around this circle and coming to the same point here, so this angle starts with here and it goes 90 degrees, 180 degrees, 270 degrees, 360 degrees, and goes again here. So it has rounded about 400. What is it? 360 plus 50, 410 degrees. So we are again in the same place there. And if we check what is cosine of this angle, cosine 410, we will get the same value for cosine as we did with the 50 degrees. And the same happens with sine, 0.766, and it is the same value as was sine 50. So this means that this and the same continues in every round. Every 360 degrees we find ourselves in the same point in the what is this in the arc of circle there. So that means that cosine and sine has a period of 360 degrees. And that is important to notice when we are solving equations where we have either sines or cosines. How about tangent? We saw that this 50 degrees had a tangent point there. If we continue rounding this angle here, now this is 50 degrees there. Now it is 90 degrees. We continue it. Now we have rounded 180 degrees. But what happens here? Now we are here at this point there, but this line goes through the same line as this 50 degrees line. So we notice that when we have added 180 degrees to the angle, we got the same tangent point there. So if we add 180 degrees to this value, we get 180 plus 50 degrees. We have angle 230, and if we take tangent of this value, tangent 230, we get 1.19, and if we put this, we got the same value for tangent 50 degrees. And again, if I add 180 degrees to this value, 230 plus 180, we get the angle 410, and if we get the tangent value of that, it is again this 1.19. So that means that the tangent has a period of 180 degrees. So I will draw that periods of sine, cos, and tan. Sine and cos 360 degrees and tangent 180 degrees. We can see also that from my Excel, which I will add this Excel to the Moodle, but I will now it is not yet there, but I will give this to you. I have made this kind of Excel. I hope can you see these numbers well enough there? I'm not sure how well you see. I've made this kind of picture or table or spreadsheet of Excel. There I have these blue numbers. There are I am possible to change them. So this means that I start with the minus 200 degrees, and as you see from the picture, this x-axis or this horizontal axis here, this is the axis which tells us the value of angle. So this picture starts with minus 200 degrees, and the step is 0.2 degrees. So as you see here, I calculate or calculate the values of sine with the steps of 0.2 degrees. So you see every the next number or the next angle is always 0.2 degrees more than the previous one. And this number there is the sine of the angle of this 0.34 approximately. And from this picture we can see that this is the vertical axis or y-axis there, and this point there is, well, it tells us also the coordinates there. It is about 0.34 from the picture. And this Excel has calculated for me, I think they are, you can see the lines there, but it is about 4,000 rows there. And then I have drawn the picture of the sine curve, and it goes like this. I could change these values there, but I'm not going to do that because I should change also the scales of these axes there. But here you can see the period of the sine, because if you are seeing that here we have this point and we are going to this line, and at this point we are at the same height again. And if we cut this part here, I will take this method here. I will cut approximately the same part here. I can't use this. It was not good pedagogical choice, but you can see that if you cut this part here and add it to the end of this part, so you get the same curve there. So this copies itself, this sine curve there. And here you can also maybe better to see that here we have the value of sine when the angle is 0 degrees, and we have here 350 degrees. You can see the 360 there, but it goes through the horizontal axis in the place where the x-coordinate is 360 degrees. So this tells us that the period of that function is sine functions is that 360 degrees. Then I have made another picture there with this cosine. By the way, I usually, probably this doesn't help you, but when I draw sine or cosine curves, I usually choose the color for sine, and I always take blue color for sine, because that helps me to remember which curves they are, because in Finnish sini means the same as blue. Sininen is the color of blue in Finnish language, so it is easy to help to see that this is actually, when I'm watching my own drawings, I see that this is sine there. And but then this cosine again, the same here. I have drawn the curve of or cosine curve there, or Excel has drawn that picture there, and we see that it looks like very similar as this sine curve there. I will change the view. Here is the sine, here is the cosine. They are a little bit different. I will take the same zoom % there. Now probably we can see better. It is the same figure there, but it is in the different place. So they look like similar, but they are in the different phase. The cosine curve is a little bit to the right or to the left from the sine curve. And here also you can see the period there. For example, here if we have 0 degrees, the cosine is exactly 1. We could see that from this unit circle. If we have the angle 0, then we are lying in this x-axis, and the cosine gets the value of 1, and sine gets the value of 0 because it's the coordinates of this point. And now I try to get the picture again there. And here you can see that here the cosine gets the value of 1, and here again it gets the value of 1, and you can probably approximate that it happens in the place where the angle is 360 degrees. We can also watch the values there from the table. This axis is the angle axis, so angle column, and if we get to the angle of 360 degrees, we can see that, where is it? Here we can see 360 degrees gets in 360 degrees the cosine gets the value of 1. And then the last one, actually in this Excel sheet there are many other pictures also. I have drawn the same figures with unit of radians. If we calculate the angle in radian units, then the figures, well, they look similar, but of course the x-axis is the different because it is the radian value. But now I will take. Oh, here I had this picture where there was both sine and cosine. So this blue line here is sine curve, and the red one is cosine curve. So you can see they look like similar, but they are in a different phase there. But then tangent, this is totally different looking curve. It is not this kind of smooth sine or cosine curve, but it is this kind of uncontinuous curve. Actually, these vertical lines there, they actually don't exist in the picture. This Excel draws that picture. It is not possible to take those away. But these lines just tells us that these vertical lines there, they don't belong to the tangent curve. Tangent curve is only these rounded curves there. But you can see that these vertical lines there, they are some kind of asymptotic lines there. So this tangent curve here comes all the time nearer to this kind of asymptotic, or it is not tangent line actually, because this is the tangent curve there, but this tangent curve is going all the time nearer and nearer to that vertical lines, but it never touches it. It never crosses that vertical line there. There is this kind of discontinuity point there in that place there. So it goes upper here, and then it jumps over to this vertical lines, and then it starts again from the bottom, and thus then again it goes higher and higher and higher, and all the time when it goes through this vertical line, it or again drops to the bottom of the curve. So this is the figure which tells us which kind of figures those tangent lines, those tangent curves give us. why is there these kind of discontinuity places there in tangent? We can see it from let's see first the period of this tangent line. We can see that it goes through origin here. Next time it goes, so remember this vertical line, it does not belong to the tangent curve. Here it goes again through the horizontal axis, and you can see that the coordinate for x coordinate for that place is 180 degrees. Let's see from this column there, 180 degrees. This is a Excel uses this kind of exponential form. There is some kind of rounding errors which happens in using Excel. This value here is minus 7.8 times 10 raised to the power of minus 14. So this is actually minus 0.000000, etc., so that the 14th decimal is the 7 and 15th decimal is the 8 there. So this number actually means that the value is exactly 0, but this comes from some kind of, I think it has something to do with the number system which in computers when they use binary numbers, and probably that's the reason why it doesn't give us the exact value of 0. I don't know, maybe one of you may know better than me, but let's just assume that this means exactly 0. As you can see, the numbers in above and below it, those numbers are very near zeros. So this number is exactly 0, even though it doesn't seem like that. But from the picture, we could see that from in the place of 180 degrees, this tangent lines goes through the horizontal axis. So this tells us that the period of this tangent is this 180 degrees. I will add this Excel there. You may also choose to change the values there and check what kinds of figures you get there. Okay. And let's now we had this title trigonometric or trigonometric equations there. Oh, I forget to show you that this discontinuity places there in the tangent curve. So these vertical lines there, you can see it is in the place of 90 degrees and 270 degrees. What happens there? If we have this angle here, it starts with, I will take this away. It starts with 0 degrees and it goes up, and you see we are now discussing of tangent, and the tangent value is the height of this point here, which goes through this, which goes in this along this tangent line there. So this the height of this point with my pen is the value of tangent, and now it goes, like you can't see anymore, it goes high there, and the angle goes there upwards. Probably now the tangent point there is probably in the roof of my house there, and now it goes all the time higher and higher and higher and higher, and now it is probably in the moon, and now it is in a Saturn or Pluto or Andromeda or where that may be. But you can see that this you can you can change the value of the angle so that you all the time get nearer to 90 degrees, but you don't actually get that value there. It is 90 degrees, but you are going all the time nearer and nearer, and the tangent point raises all the time higher, and it can get whatever value you want. If you want to get a tangent value, for example, 3 million, you just take a value, take an angle which is very near 90 degrees, but a little bit below it. And from this picture, again, I will show you that when we are going near the 90 degrees, here you can see, here is 89 degrees, the tangent value is 57. 89.2, now it is even already 71, 95, 143, 286. And now this value actually, this is the reason why the Excel draws the line there, in this vertical line in the picture, even though the tangent is actually not defined in the place where the angle is 90 degrees. But if I change a little bit, I can draw type here an angle which is very near 90 degrees. I will take, for example, this kind of angle there, and now you see this over 5,000. Let's add decimals there. Now it is 57,000. So you can imagine that you can get whatever value you like if you just change the value near to. Oh, I made a mistake there. I have to correct my table. So this was the line number I wanted to change. So you can get a very, what does it? It doesn't show all the decimals there. So this was the value I typed there, and it is over 5 million right now, the value of tangent. Okay, now we finally can try to solve some trigonometric equations, and I will take an example, and this some kind of introduction to those equations. This told us that these sine, cosine, and tangent, they all have periods. Sine and cosine had this 360 degrees, and tangent has this 180 degrees period there. So when we are having an equation and we are not solving the problem which is concerning triangles, then we always have to take account that these solutions for these trigonometric equations, there are infinite numbers of solutions, because there is that period. You can always get the same value for sine or cosine or tangent when you go through this circle there, and all when you have this period of 360 or 180 degrees period there. So now finally example. Solve for x. Oh, sorry, no, let's not put x, because many times x in mathematics or technology, when we are solving problems concerning sine, cosine, and or tangent, many times this x means radians. And right now I want to solve this equation so that we are using degrees. So solve for alpha. and the equation is sine alpha equals 0.237. And remember, this is not a triangle we are solving. This is not an angle of a triangle, but it is a solution of this equation. So first step is again also always that we are using some calculator or Excel or something some calculator machine which gives us one solution. So in this place, first step, calculator, and then there we use this inverse sine. So we get inverse sine of the 0.237. I don't know how many times it happens, but these numbers we all probably are so used to our numbers in our own language that many times I think I may do so also, so that when I am speaking in English I may choose the names of the numbers in Finnish language because I'm so used to say these numbers in Finnish language. So it is always very hard to probably one of the hardest things in mathematics is the use English language for numbers. And now I will take the calculator and check what is the angle which gives us sine value of 0.237. So we will take sine minus 1 or inverse sine, and this will give us 13 point. I will take some decimals there, like this. Let's check this from unit circle. If we have sine value of this kind of number, and sine is the y coordinate, so in this picture here we have 0.1, here would be 0.2, that would be 0.25, and this 0.237 is a little less, so it is somewhere here. I try to, let's take from here 0.1, 0.2, 0.25, so it is somewhere there. How do I do that? I shouldn't have done this. 0.1, 0.2, 0. It is about here, and the angle here tells us it is about probably 13 degrees there. And well, it was almost 14 degrees there, as you saw. Well, this was not so easy to show with this poor picture, but that tells us that the angle is about 13 degrees, and now we see it is exactly 13.7 etc. degrees. But this is not the only solution. Sine has period of 360 degrees. So the solution is, I have to use a different, because I want to use alpha here, but let's say this is, for example, alpha 1, so we don't mix it with the solution of the whole solution for the whole problem, for the whole equation. So we have this value there, and then plus minus n times 360 degrees. And here n equals 0, 1, 2, etc. So that means that we can put whatever integer in the place of n there, and always we get the solution for this problem. So for example, this is the final solution. If this is very easy problem, we can, today we don't have so much time, but I think next time I will take a more complex equations there, because this is not always, it is not always as easy, but if you can solve this, you have possibilities to solve also those more hard ones. For example, let's choose n. I will help use my Excel. Sorry about, you can't see now my paper, but in Excel I can use random number, in Finnish satunnaisluku väliltä, or in English random number between those values I am giving. I will take 1 and, for example, 1, 4, 5, 6. So this will give me random values there, and I'm pushing the button F9, and it gives all the time a new random number there. And I will watch, and I will take the value it get. So it get us 91. So let's assume that the n is 91. And now we have the alpha value there. The formula there is like that. We can take 0.70, sorry, 13.70954, etc. plus 91 times 360 degrees. So this means I will calculate the value of that angle. Sorry, it was in this calculator. I had this value of this angle. So I will add the 91 times 360 degrees there. So I will get the angle of 3277.0955 degrees. And after that we check what is the value of the sine. Of course, we all believe that it will give us the correct value, but you never can be sure. And now I will take the sine value of the answer. From many calculators you can pick the latest answer to the future calculation, so you don't have to type that anymore. So it will take the sine of this angle, and as you see, it gives us this 0.237, so as it should be. And we are so happy because of that. I'm a poor painter, artist. Okay, that was the sine equation there. This was sine problem there. Did I do this correctly? Because now when I watch again this unit circle, this is very important, this unit circle, because it helps you to check your calculations and also helps you to find all solutions for the problem. We had this equation here that told us that the angle is, this angle alpha is such angle that the sine of that angle gives us 0.237, and we checked that angle there because there was the height of the point is there, and I approximated that the angle there was about this 14 degrees or 13.7, I guess, was the more exact value, because the height of this intersection point was this 0.237. But is this actually the only solution? Of course, we have this period here, 360 degrees. We have taken that account. I made that here. But is this all? Are there other solutions also? Are there other points there which have in the circle which have y coordinate the same as this point here? If we go through this line here, we see, or this curve here, we see that now y coordinates all the time rises. Now it is 1. Now it starts going lower. Now it is about 0.8, and somewhere here it is 0.5, and about here it is again at the same height there. And this point is also the solution, or this angle here is also the solution for this problem. So the first solution we got was, do I have any? I will use this. Was this about this angle here, and the other solution is this angle there. They both get the same value of y in the circle there. How do we solve that? How do we solve this problem now? The problem is that this calculator only gives one value. If we get this inverse sine of this 0.237, it gives us only this one solution there. But we can see from this unit circle that there is also another solution. This angle here is the same as this 13 degrees here. So we see that this is 13 or 13.7 degrees. So the angle from the x-axis and to the counterclockwise direction is this angle. Over 90, not yet 180, but this degrees below that or short of that. So the other solution it is that we get the angle of 180 minus 13.7 degrees. Wait a minute. We have more solutions. From the unit circle, we can see that also angle 180 degrees minus, what was that, 13.070 954 degrees gives the same value of sine. So I will calculate this. I made the subtractor in the different order, but let's forget this minus sign there. This is the other angle, 166.29045, etc. degrees. And this also has this period of 360 degrees, plus minus n times 360 degrees. So, but are there any other options? Let's be sure not to forget anything. There are no other solutions, because we can find 2 points from the circle which has the same y coordinate. There are only 2 points in the right hand side of the circle and in the left hand side of the circle. There are no other choices there. So the final for the equation, what was the equation? Sine alpha equals 0.237 is and the other one is this here. Of course you could round that number there if you like, but so there are these are all the possibilities. I will show again you the Excel sheet, because from that we can probably see more than from the unit circle. We'll try to find my Excel again. Sine. Here I will do some changes there. Maybe it's easier to see if I make 20 units there. No, it is not good choice. Or can I make this a little bit bigger? Here we can see. This is probably a little bit more. This is this sine curve there, and the equation was sine alpha equals 0.23 there, and this is the y-axis there, and this 0.23 is about here would be. I will make this bigger. Don't understand what is the problem with this. Sometimes this is so. Can't find. you couldn't believe that I use Excel Excel a lot. I'm one of the most Excel using teachers probably in the whole university, but right now I can't get it work. Okay, let's forget that. But we have this 0.23 is about this height. So here we find first solution. It is about here. And if we watch the angle there, it is about, from my picture, this is very inaccurate, but about 15 degrees probably. And as we remember, we had this one solution what was this 13.7 degrees. When is the curve next time in the height of 0.23? It is about here. And from this picture we may approximate that this may be about 160. You can see those coordinates from picture. It sometimes tells those coordinates there. This is about at the maybe a little bit lower there. This is so. No, it is quite correct there. I don't know how well you can see those numbers there, but now it tells that the sine of this 166.2 degrees equals 0.238. So this is the approximate solution. And that was the other solution there we had. And when we have this period of 360 degrees, then both these points here are those first points there, and every time we add 360 degrees or we subtract the 360 degrees of those values, we are at the same height. Here would be the third solution about here, and it is probably, can I see those coordinates there? About here, about 373 degrees gives us the same value for sine. Okay. This has been so hard lessons that I am totally exhausted here. Thank you. There is some kind of applications there, and there is some music also. Yes, okay. I thank you for there is in the chat box there is one link. I have to check that. Thank you very much. I think I will end right now because we don't have so much time to next example. Next time I will continue with these trigonometric equations, and I will take the more complex equations. I hope we will get more done next time, because we don't have to use the time for these introductions, and we now somehow understand how sine and cosine and tangent works, and how we can use this unit circle when solving these problems. I hope we will be better next time. But I will add this Excel sheet there in the material, and you may check if you find that important or interesting. And there are also these assignments, not concerning these yet, but I will add quite soon. I'm not sure. I don't know the date, but I will make there some assignments which concerns these trigonometric equations also, but probably not before next week's lessons, because I want to go through these more complex equations with you. But continue with those assignments, and that problem I showed you in the beginning of these lessons, and it was also in the, or it is also in the chat box there. I will use that again. This is quite nice problem. I found this or not exactly this problem, but this is almost same as these area problems I showed you earlier. But this is a problem where those numbers in the picture, those are perimeters of those, not areas, but perimeters of those rectangles. And if you like to solve these kind of challenges, you may solve them. You may find this from this chat box of this Teams meeting, this same challenge there. But I think we have got enough of each other today, and maybe we will end right now. I will sit here to the 2 p.m. So you may or also during evening you may send me messages and ask help, or let me check your assignments. But I will end my talking right now, and I wish you happy evening. Bye bye.